All right, welcome to the last section of the chapter. This is about arc length. Arc length. So this one's a little bit more straightforward as there is a formula, but I do want to show you where that formula comes from and how to apply that formula, and really to check to make sure that your answer is reasonable. So looking here, you can see that I have what would have been your do now if we were in person. I will point out that a lot of times AP, when they get into volumes rotated about an axis, will introduce an axis that is a non-major axis. So like rotating around the line y equals 2 is a common type of problem. That's that. All right, cool. I will also point out that the lengths of curves, once you get the formula filled out, it is kind of difficult to do the integration. So most of the time, whenever I've seen an arc length problem on an AP test, it has been set up an expression, but do not evaluate it for the length of blah 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 blah. So this particular problem might be just set up an expression for the length of the curve y equals sine of x from 0 to 2 pi, but do not evaluate it. But before we get to figuring out what the length of this curve is, we are going to draw the curve. And we know that sine of x has a period of 2 pi, so up and down. There's one period of our function from from 0 all the way up to 2 pi. And again, that's just because I know what the graph of y equals sine of x looks like. Now, the first thing that I'm going to do here, I'm not going to say what the length is, but I'm going to say what it's more than. So we can see that from 0 to 2 pi, the linear length from 0 to 2 pi is going to be 2 pi. That's just the shortest distance from 0 to 2 pi. So I know that the length of this curve has to be bigger than 2 pi because we've kind of stretched out that x-axis and made an uppy part and a downy part to this. I don't know exactly how long it is, but whatever my answer is, it better be bigger than 6.28 or else I did something wrong. So one way that I can do this, I can go through this, arc and I can just draw in straight lengths. So looking there, if I had straight lengths that looked like this, I could add those. It looks like I only have 4 lengths together. If I add those 4 lengths together, I could actually get what the length, the approximate length of the curve. Again, since we have away from the curve here, it's not going to be perfect, but it's closer than saying it's about 2 pi. Now, if I put in more lines than this, I could get a better approximation. Put more lines in, better approximation. Until I get the infinite segments, that's going to be my best bet. So that's kind of drawing our mind to the where this is going. So now I can go in here and I can draw in different components to this graph. So what I'm drawing here is all of the horizontal distances of those black segments right there. And now I'm going to go in and I'm going to draw the vertical components of those black segments right here. So vertical component, vertical component, vertical component, and vertical component. And now we can actually see that all of those segments produce right triangles in each individual segment. Now look in here, I can go in and I can see that this distance right here is delta x1, delta x2, delta x3, and delta x4. And again, in order to make this even better, I would want to have like, I don't know, a bajillion delta x's. Now also, I have delta y1, delta y2, delta y3, and delta y4. And to get this even better, again, I would want to have a bajillion delta y's. Now, why do I do this? Because now I can see that this first segment right here would actually be able to be produced using some very basic math that we learned way back in, I don't know, like 4th or 5th grade. Our total length is just going to be the sum of each of these black segments. And each of these black segments is a hypotenuse on a right triangle. And we know in right triangles that we have our hypotenuse squared is equal to the sum of the squares of the two legs. In this case, each of our segments is going to be equal to the square root of the sum of the squares of the two legs. So looking back over here in this expression, this is going to be, for our first segment right here, it's going to be the square root of delta x1 squared plus delta y1 squared. That's not the only segment that we wanted. We wanted to have another segment where we would have the square root of delta x2 squared plus delta y2 squared. Again, we have 4 segments that we want to tackle here. First segment, second segment, we got a third segment. It's going to be the square root of delta x3 squared plus delta x4 squared plus the square root of delta x4 squared plus delta x, why am I saying delta x? Delta y4 squared. All right. So here again, we don't want to have just 4 segments, we want to have infinite segments. But however many segments we have, we know that we can just rewrite this as, instead of adding all of them individually, we can use the shorthand of just sum the square root of, here now we can just call it delta x squared plus delta y squared. So that allows me to write as many segments as I want in really shorthand. Now I'm going to try to modify this, this expression to make it more evaluatable. Because ultimately, we know that we want to have infinite tiny little segments here. And when we make infinite tiny little segments, this is going to become our integral symbol. Well, we know in order to have an integral symbol, we also have to close out with a differential. So we know that this problem is going to have a delta x at the end of it. So I'm going to just do some fancy math in order to get a delta x over there. And the fancy math that I'm going to do is just write it over here. Now I'm not allowed to do that because that changes the quantity of this expression. In order to multiply a delta x on, I also need to divide a delta x off. All right? So now I look a little bit closer here. And that delta x in the denominator, I don't like it looking like that. I want to slide it underneath of the square root so that I can start making this a little bit simpler. So I know that this is going to be equal to the summation of the square root. And to get that delta x underneath that square root, again, if I want to make it under a square root, I have to also unsquare root it. So the denominator here is now going to become delta x squared. So now I've got numerator stays the same, delta x squared plus delta y squared, and this delta x still hanging out outside the radical, right? So now, since I have my sum in my numerator here, I can actually rewrite the radicand of this problem as delta x squared over delta x squared plus delta y squared over delta x squared. So in that step, I really didn't do anything. All I did was split the fraction up. Now I'm going to simplify those two fractions. First fraction, I see a number divided by itself, right? So this is going to become summation of the square root of number divided by itself. That's just 1 plus, well, I see that the numerator and the denominator here are both squared. I can rewrite that as delta y over delta x squared. And delta x is still going to hang out here. Now, if I want to rewrite this as an infinite sum, again, my Greek letters change into their Latin equivalents. So the Latin equivalent of sigma is that s. The integral of 1 plus, and our Greek delta changes into the Latin equivalent, which is a d squared, and the delta x again becomes dx. That formula is something that you should probably know, just like the back of your hand. Now I will point out, since we're talking about an integral, we can now put in our limits a and b, and now we can actually find out what the length of the curve y equals sine of x is from x equals 0 to 2 pi. Because I know this expression, dy dx, that just means find the derivative. So if I want to find the length of this curve, the first thing that I do is I find dy dx, and dy dx, y was sine, so the derivative of sine is cosine of x. So the length of my curve is going to be the integral from the beginning to the end of the square root of 1 plus dy dx squared dx. So there's our expression for the length of the curve. Again, on the AP test, what I've seen most often is write an expression but do not evaluate for the length of the curve, blah, blah, blah. Now here, since we actually want a value, it probably would be beneficial for us to find that out. Once you get this expression on your homework, this particular section, you should definitely use your calculator for. From 0 to 2 pi of the square root of 1 plus cosine of x squared dx, and 7.640. Approximately 7.640 units. Again, since we don't have a length here, we're just going to say 7.640 units. Now looking at this, again, we started off by saying that the answer has to be bigger than 2 pi. Just some quick error checking allows me to see, yes indeedy, this is bigger than 2 pi, because again, 2 pi is 6.28 something or other. Which just makes sense. This should be bigger than the linear distance. Take away the calculator, and not what I wanted. That's what I wanted. So here's another way of setting up the formula. It's pretty much the exact same thing, except I like to deal with the tangible before I move into infinitesimal. This setup really just used the infinitesimal to get the problem, but you can see the math is exactly the same. This part is the super important part. You need to know the formula. The length of a curve is L is equal to the integral from a to b of the square root of 1 plus dy dx squared dx. It is possible to do this in terms of y. I'm not going to really tell you that right now. That comes a little bit later. But if a smooth curve begins at AC and ends at BD, where A less than B and C less than D, then the length, arc length of the curve is L is equal to the integral from A to B of the square root of 1 plus dy dx squared dx, if y is a smooth function of f on A to B, and it is L equals the integral from C to D of 1 plus dx dy squared dy if x is a smooth function of y on C to D. And again, we'll get to why we would use this second option, but that second option, things to note, if you're doing everything in terms of y, you're taking the derivative with respect to y, and you're using your y coordinates as your limits there. All right. Again, we'll get into why we would do that, but before we do that, here's a very straightforward one. Find the length of the curve, y equals x squared for 0 to 1. All right, so again, I like to draw the picture just because it really drives home what the graph looks like. We're talking about x squared, so I don't even need my calculator for that one. I know that I'm talking about from 0, 0 to 1, comma 1. So one thing that I do like to do here, I like to evaluate the linear distance. So the linear distance here is going to be, let's see, just drawing in my right triangle. The linear distance from the beginning of the interval to the end of the interval, I just call that d, is equal to the square root. And you can use the distance formula, but really the distance formula is just the Pythagorean theorem. It would be the square root of 1 squared plus 1 squared. So I know that the answer has to be bigger than the square root of 2. And square root of 2 is just 1.414. So I know that the answer has to be bigger than 1.414. So this step right here where I say that the linear distance is square root of 2, not necessary, but it allows you to error check when you finally get into the length portion. Now to find the length, again, part of the formula is dy dx. So I would insist that you write out what the derivative is. Don't try to just jam it into the formula. Here we have dy dx is equal to, oops, almost forgot what the derivative of x squared was. It's 2x. So now we know that the length of the curve is equal to the integral, and since we're doing everything in terms of x here, we're going to use the x coordinates. So from 0 to 1 of the square root of 1 plus dy dx squared dx. So again, once you get the derivative, it's just slam it into that formula of integral from a to b of the square root of 1 plus the derivative squared dx. And now here we would probably want to, again, on the AP test, you wouldn't be required to give a numerical answer, but here we want to give an answer. So alpha window 4 from 0 to 1 of the square root of 1 plus 2x squared dx. And something of note there, make sure that the entire function is inside the parentheses. That 2x is what I'm talking about there. And we can see that our answer, again, is bigger than square root of 2, so it's an answer that makes sense. We would say that this is approximately 2.479. 2.479. So again, you can tell that these are pretty straightforward. Going a little bit further here. I said going further. That's the checking reasonableness, is just looking at the linear distance. So looking here, same exact thing. Again, checking the reasonableness. I like to do that first. I meant to do that in red, just to keep it separate. Checking how reasonable the answer is. Again, it lets me see if I did something dumb here. I can see that one of my side lengths is 3, my other side length is 9. So the linear distance is just going to be the square root of 3 squared plus 9 squared, which would be square root of 9 plus 81, square root of 90, which, heck, I don't know what the square root of 90 is. Who the heck knows what square root of 90 is? Oh wait, I do. 9.487, 9.5. It's got to be bigger than 9.5, whatever answer we get here. So again, I start off by calculating, oops, we got to switch back to blue. Go back to blue. dy dx is equal to, finding the derivative here would be, oh, I think that's just negative 2x, right? So now we can see that the length is going to be the integral. Since we're doing everything in terms of x, because I haven't told you when you would want to do it in terms of y yet, we're going to go from 0 to 3 of the square root of 1 plus negative 2x squared dx. You can simplify this if you want to. I wouldn't, just because, I mean, I can just plug this into my calculator and be like way easier. So looking here, alpha window 4, going from 0 to 3 of the square root of 1 plus negative 2x squared dx. Again, noting that I did use my parentheses around that negative 2x just so that I don't screw anything up here, and 9.747. 747. And again, we know that that is reasonable because over here we had the square root of 90, which last time I checked the square root of 90, you can see it's on my screen now, a little bit less than 9.5. So 9.747 makes sense. It is reasonable. Again, you don't have to check the linear distance, but it allows you to see if your answer is completely dumb. Looking here, we have the, we want to find the arc length of this from -1. We want to find the arc length of the entire blue right here. So first off, we do know that our linear distance, we can actually count it off right here. Our linear distance in this problem is just going to be 2. So we know that our answer has to be bigger than 2. By the way, there's a much easier way to do this problem. So if you see it, I would normally say don't call it out yet, but you're not here, so it doesn't matter. In order to do this problem, I do know that I need to solve this equation for one of the variables, and here's where you can get some freedom. If it's easier to solve for the y variables, then you would want to do this. This is the first example where you could do this in terms of y. But I see here, if I was to do in terms of y, we wouldn't actually have a function. I would want to do everything in terms of x. So I'm going to solve this for y. Just subtracting x squared. I get y squared equals 1 minus x squared. Square rooting, we get y is equal to the square root of 1 minus x squared. Looking at the function, I can see that it is just the positive portion of this curve, so I'm only doing the positive portion of this curve. Now I do want to find dy dx, which is a little bit more difficult in this situation because we're dealing with square roots. But we remember from the other, not the other chapter, we've done so many chapters. Chapter 3, oh my goodness. When we take the derivative of the square root, it's going to be 1 over 2 the square root of the stuff times the derivative of the stuff, so times -2x. Looking at making that a little bit more simple, the 2's can cancel off. I'm left with -x over the square root of 1 minus x squared. So there's my derivative. Now looking here, my arc length, again, my arc length is always the integral from a to b of the square root of 1 plus the derivative dx, squared dx. So looking here, I know I'm going from -1 to 1 of the square root of 1 plus derivative, copier over here, square it, and then dx. And you could simplify that. I hope you recognize that that's not the simplified version of the expression, but I don't care about the simplified version because all I'm looking for is something that I can plug into my calculator. And I indeed can, from -1 to 1 of the square root of 1 plus. Now here, I'm putting that in parentheses. I'm just going to write down exactly what it is. -x over the square root of 1 minus x squared. Square it, and then dx. And we wait around for a good minute or two for it to calculate. Man, your calculator's taking forever to calculate this. There we go. 2.950. And now I'm realizing I made a really dumb mistake. If you notice in my calculator, some of you might be looking at your calculators and saying, what? This does not look right according to what I have in my calculator. We can see that I should have done the 1 minus x squared. So that means this answer is wrong. My bad, y'all. Just going back up here. Whoopsies. No, we're still here. Okay, cool. So looking here, I know that I wanted to make this into a square, so What? It won't let me square in here. Maybe that's why it didn't show up originally. So what we're experiencing here is our calculator just can't handle, our calculator here, you can't handle what an x squared in here. We've just gone too far down into the nethers of plugging stuff into our calculator that we need to find a different way to do x squared. So I just changed that into x times x. That's what x squared means anyway, isn't it? And now we're gonna have to wait another couple minutes for this to go through. Full disclosure, I did just pause the recording and sat here for like a minute while my computer thought about this one. So we can see that our answer is approximately, this answer sounds a little bit better, 3.142. Wait a second. 3.14158. That looks very familiar. That number, oh, wait a second. Looking over here, we can see that this is just the equation of a circle centered at the origin with a radius of 1. So the arc length, another way to get this would just be the arc length is equal to 1/2 of the circumference. Our circumference here is 2 pi times our r. Half of 2 is 1 times pi times 1 gives me pi. So we can actually see there's an easier way to do this problem. Had we thought of that being a half circle. If we didn't think of it being a half circle, of course we would have to do the calculus. And plus, the calculus is just fun, so why not do it? So I guess my caution here is really be wary of your calculator not being able to handle stuff here. Make sure that you type in everything correctly. All right, so now we're going to find the length of the curve, y equals x to the 1/3 power between -1, -1, and 1, 1. First thing that I'm going to do here, oh, you might want to see the whole problem, right? First thing that I'm going to do here, I'm going to graph this function. Let's move this over here so I can pull up the calculator. And I can see, let's see, whoopsies. Technical difficulties, sorry about that, guys. I go into my calculator, and I do x to the 1/3 power. I'm graphing from, what was it, -1, -1 to 1, 1. So I'm going to really restrict my window from -1 to 1. And from -1 to 1, I'm going to graph it. All right, that's what it looks like. I'm going to sketch that over here now. So sketching that, I know that I'm going from, why would I have to sketch it? I have it up on my, so looking there, I can now figure out my derivative. So my derivative, my dy dx, is going to be equal to 1/3 x to the -2/3 power. So I'm going to try this out and see if it works. And now I'm going to have the length is equal to, since I'm dealing with my my x's here, since this is in terms of x, I have to use my x values here. So it's going to be the integral from -1 to 1 of the square root of 1 plus 1/3 x to the -2/3 power squared dx. And now again, just like last time, I'm going to try to plug that into my calculator. So here I go to my, all right, here we go. Alpha window 4, we've got from -1 to 1 of the square root of 1 plus 1/3 x to the -2/3 power squared dx. And I'm going to scour through this to make sure that I actually plugged it in correctly. And there we go. I'm going to hit enter, and I'm going to, whoa, wow, that was fast. We have a domain error. I anticipated a domain error, but I didn't think it was going to come that fast. So why do we have a domain error? The reason we have this domain error is because in the original function, we had a vertical tangent. right over here at x equals 0. We had a vertical tangent. So we had a non-differentiability. When we have a non-differentiability, we have to look at this a different way. So what we have to look at here, since that non-differentiability occurred, by the way, if you didn't see that there was a non-differentiability when you started this problem out, you can actually tell that the non-differentiability occurs at 0 because we have a negative power, which pushes my x into my denominator, and if I divide by 0, again, that makes something undefined. So here I have to look for some way to get around that vertical tangent. And the way that I'm going to get around that vertical tangent, I'm going to take y equals x to the 1/3 power, and I'm going to solve it for x. I'm going to get it in terms of y. And it's really easy to get this in terms of y cubed, and we have y cubed is equal to x. And now actually this is an even easier derivative to find. We want to find the derivative of x with respect to y, so it's going to be dx dy, which here, derivative of y cubed is 3y squared. So my arc length here is going to be equal to the integral, and now since we're doing this in terms of y, we want to use the y coordinates, which kind of sucks in this situation considering the x's and the y's are exactly the same, but but just be aware that I'm using the y coordinates here. So from -1 to 1 of the square root of 1 plus dx dy squared dy. So here's your first encounter of when we should use in terms of y. If one of those non-differentiability occurs, if one of those non-differentiabilities occur. So another option would be if it's easier to solve for y, of course you would want to do it in terms of y. But anyway we look at it, we want to plug this into our calculator. So I'm just moving that so that I can see on my own screen here. On my home screen, I know now I have to do the integral from -1 to 1, acknowledging those are the y's instead of the x's, of the square root of 1 plus 1/3, 3. And you could put a y in there, but it's really just easy to put in. Did I forget something again? I forgot the squared in here. I forgot the squared. I gotta make sure it matches. Luckily I caught that before I typed it into my calculator. 3x squared dy. And it looks like our arc length is 3.096. Approximately 3.096. And now for something, there we go. Determine the length of y equals 2/3 y minus 1 to the 3/2 power from 0,1 to 1810. Now looking here, it's already solved for x, so I'm just thinking maybe we can just leave this in terms of x. Here we do know that we want to find dx dy, which in this case would be, let's see, 2/3 is a constant multiple. The 3/2 is going to carry down, so 2/3 times 3/2 times the quantity of y minus 1 to the 3/2 minus 1 gives me 1/2 power. All right, cool. So there's my derivative. I can see I have no negative exponents, so I'm not going to get that vertical tangent off of this. Further, I can see these 2's and these 3's cross off, and now I can get really easily that my arc length is equal to the integral from something to something. Now here, since it's in terms of y, I'm going to use my y's. I'm going to go from 1 to 10 of the square root of 1 plus y minus 1 to the 1/2 power squared dy. Okay, well that to me draws some issues here because I see that 1/2 and that squared. That's a square root squared. So I'm not touching my calculator yet because I see some fun stuff happening here. From 1 to 10 of the square root of 1 plus half power and second power cancel off. We have y minus 1 dy. And now I can see that this is going to be equal to the integral from 1 to 10 of the just square root of y dy. So now I get into a place where I could do this by hand if I wanted to. So here's a nice friendly problem. But why would I want to do that when I've already told you guys that this bad boy is completely acceptable on everything this section? So let's just use a calculator. We know we're doing alpha window 4, integral from 1 to 10 of the square root of y dy, and we can see approximately 20.415. Approximately 20.415. Approximately 20.415. So there's two cases where we would want to use things in terms of y instead of in terms of x. Again, if you have a vertical tangent or some sort of non-differentiability, or if it's easier to solve for x there. And I said advance. And advance again. All right, cool. So last thing that we have here, find the length of the curve. Y equals absolute value of x squared minus 1 plus x from x equals -3 to x equals 0. Now here is another case. I'm going to call this getting around a corner. Really, it's going to end up being a cusp, but it's another non-differentiability that we have here. So the first thing that we have to do is graph this function. All right, so you can see this function. I graphed the function there. I made my window from -3 to 3 and from -5 to 5. And here's what it looks like. I kind of think of it as like that shruggy face emoticon that sometimes people put into their work occasionally. Oh, crap. Why didn't you guys tell me I didn't pull up my calculator? Okay, so there's the function. There's the window from -3 to 3, from -5 to 5. And there's what it looks like. Now again, I'm only concerned about the length from here to here. So I do not care that there's a cusp right at x equals 1. What I do care about is I have this corner that occurs right here. And that corner occurs because of this square root. The corner, or the cusp, I guess we should say, occurs when the interior to my function is equal to 0. So that's going to occur at plus or minus 1. So again, just referencing why those cusps occur. In order to get around the corner here, what I have to do, I have to rewrite this function as a piecewise function. So the piecewise function means whenever I plug in a number and I get a positive inside this absolute value, the function stays the same. So if I was to plug in a number less than -1, this would be positive. And the function would be x squared minus 1 plus x for x less than -1. If I get a negative inside here, I would have to make the quantity opposite. Negatives occur in here when I use some number in between -1 and +1. -1 less than x less than +1. And then beyond, I will have x squared minus 1 plus x for x greater than 1. But I really don't care about that beyond 1 because here I'm only going from -3 to 0. And in order to do this length, we actually have to find two dy dx's. We have to find the first dy dx for this interval, and that's going from -3 to -1. So that would be, let's see, 2x plus 1. And then we want to find our second derivative, dy dx, not second derivative, but another first derivative, where we find the derivative of this chunk, which is going from -1 up to 0, and that would be -2x plus 1. And now we're just really going to set up two different intervals, or two different integrals the length is going to be the integral from -3 to -1 of the square root of 1 plus 2x plus 1 squared dx. And then we're going to add on to that the integral from -1 to 0 of the square root of 1 plus -2x plus 1 squared dx. And then we can compute that just by using our calculator. So again, here we would have on our home screen integral from -3 to -1 of the square root of 1 plus 2x plus 1 squared dx plus the integral from -1 to 0 of the square root of 1 plus -2x plus 1 squared dx. And there's so much stuff that I plugged in there, I want to make sure that I got everything right. Yeah. Go hit enter. 8.630. 8.630. Approximately 8.630. And then we call it a day. Call it a day for everything because we are done. See you guys tomorrow.